In the deep silence between the stars, where light travels for billions of years without ever touching a world, a single photon drifts. It is not a bead of matter following a path through the dark. It is not a point on a map of the cosmos. It is a question. For in the strange architecture of the quantum realm, this photon does not reside in any single place. Its being is spread thin across a cloud of possibilities, a shimmering haze of could be and might be, filling a volume of space far larger than itself. It is like a whispered thought that lingers on the edge of consciousness, not yet spoken, not yet real. Like a coin balanced on its edge, frozen in the moment before it falls. Somewhere, a planet spins unseen. A distant star flickers unseen. The photon moves, but not in the way we think of movement. It is everywhere it is allowed to be, until the instant it meets something that demands it choose. In that moment, the infinite cloud collapses to a single dot. One place, one time, one outcome. But until then, it exists in a realm between, where location is undefined, where reality seems to hesitate, unsure of itself. A phenomenon called superposition. The most unsettling idea in modern physics. If the most basic threads of the universe can be nowhere and everywhere all at once, what does it mean for the reality they weave together? The opening years of the 20th century were an age of certainty. Physics, it was said, was almost complete. The grand clockwork of Newton's laws had explained the fall of an apple, the dance of the planets, and the curve of a cannonball's flight. The equations of Maxwell had revealed the hidden symmetry of electricity and magnetism, uniting lightning and starlight under a single, elegant banner. It was believed that the universe, like a vast mechanical watch, was governed by fixed and knowable rules, rules that could, in principle, predict every tick of time, every motion of matter. In lecture halls, some scientists dared to declare that physics was a finished story, that all that remained were details, polishing the edges of a completed truth. And yet, in the quiet corners of laboratories, cracks in that certainty were beginning to show. In 1900, Max Planck, working in Berlin, was studying the spectrum of light emitted by heated objects. For years, physicists had puzzled over the so-called ultraviolet catastrophe, the predictions of classical theory that a glowing object should emit infinite energy at short wavelengths, an impossibility. Planck's solution was drastic. He proposed that light could be emitted only in discrete packets of energy, quanta. A desperate mathematical trick, he thought. But it worked. 5 years later, Albert Einstein took Planck's quantum and gave it physical meaning. In explaining the photoelectric effect, he showed that light itself behaved not merely as a wave, but as a stream of particles, photons, each carrying a single quantum of energy. It was the first crack in the old worldview, the first suggestion that light and matter might not belong cleanly to the categories nature had seemed to assign them. But this was not the first time light had defied easy description. A century earlier, in 1801, Thomas Young had performed a deceptively simple experiment. He directed light through two narrow slits and watched as it struck a distant screen. Instead of forming two bright bands as particles would, the light produced a series of alternating bright and dark fringes, an interference pattern, the signature of waves overlapping and cancelling. It was a quiet, visual proof that light was a wave rippling through the ether. For 100 years, Young's experiment stood as a triumph of the wave theory. But the revelations of Planck and Einstein demanded a strange reconciliation. Light could behave as a wave, yet also as a particle. How could it be both? By the 1920s, new voices were drawn into the puzzle. Niels Bohr, working in Copenhagen, used quantum ideas to explain the structure of the atom, electrons orbiting in fixed, quantized shells. Werner Heisenberg, with his matrix mechanics, and Erwin Schrödinger, with his wave equation, sought to give mathematics to the strange duality emerging at the smallest scales. It was Schrödinger who suggested that perhaps matter itself, not just light, might have wave-like properties. In Paris, Louis de Broglie proposed that every particle carries a wavelength, determined by its momentum, that an electron in flight is as much a wave as a stone dropped into water. The idea begged for proof. And so the double-slit experiment returned, but this time the slits would not be illuminated by light. In 1927, experiments with electrons revealed something no one had truly expected. They too formed interference patterns. When fired toward the slits one at a time, each electron still built up the same wave-like distribution on the screen. Somehow, each particle behaved as though it had passed through both slits at once, interfering with itself. It was a quiet, almost unremarkable sight, pale lines on a screen. But behind it lay a truth that strained the fabric of reason. The only way to preserve the comfort of classical thinking was to suppose that each electron traveled one path or the other, and that the interference arose from some hidden, unmeasured mechanism. But when detectors were placed to watch the slits, the pattern vanished. The electrons now behaved like tiny bullets, striking the screen in two neat clusters. The act of observation, the mere act of knowing, had transformed the outcome. It was not a trick of instrumentation. The results repeated themselves in laboratories across the world. In the absence of measurement, particles moved as though they were spread across all possible routes, every potential journey coexisting in a shimmering superposition. Under the gaze of a detector, that cloud of possibilities collapsed to a single reality. This was not Newton's world. In the mechanics of the 17th century, objects were real, solid, and complete in their properties whether or not they were being observed. The trajectory of a planet, the path of a falling stone, the swing of a pendulum, all could be predicted with certainty if their starting conditions were known. There was no place for ambiguity, no room for probability in the bedrock of reality. But here, in the quantum world, certainty was an illusion. A particle's position was not merely unknown before measurement, it was undefined. The universe, at its most fundamental level, refused to commit until the moment of observation. This revelation unsettled even the brightest minds of the age. Albert Einstein, who had helped light the path to quantum theory with his explanation of the photoelectric effect, now found himself standing in its shadow. He could not accept that reality was governed by chance. To him, the moon was there whether anyone looked at it or not. Physics, he argued, should describe an objective world, existing independently of measurement. His words carried both frustration and defiance. God does not play dice with the universe. But others saw no alternative. Niels Bohr, the quiet but unyielding voice.
The implications were almost unbearable. It seemed that the universe did not maintain a single, objective history, but held open a spectrum of possible pasts, waiting for the moment of measurement to decide which one had been true all along. Here was the fault line that divided classical certainty from quantum strangeness. In Newton's world, reality existed in full whether or not it was observed. In the quantum realm, reality waited for the question before offering an answer. And sometimes, it seemed, the question reached backward in time. To the public, such notions sounded like mysticism. To physicists, they were inescapable consequences of the mathematics that described the quantum world with unparalleled accuracy. In this new reality, the particle was no longer a tiny solid bead of matter. It was a probability distribution, a wave function, a mathematical object that told not where the particle was, but where it might be found. Between measurements, it was nowhere in particular, and everywhere it could possibly be. This was the shock, not just that the universe was stranger than expected, but that it was stranger than could have been imagined. And beneath the awe and the discomfort lay a deeper, more haunting question. If observation could shape the behavior of a single particle, could it also shape the fabric of the cosmos itself? By the middle of the 20th century, the double-slit experiment had become more than a curiosity. It was a quiet window into the most unsettling truth physics had ever uncovered, a truth too persistent to be dismissed. The question was no longer whether particles could exist in many states at once, but how far this strange behavior extended, and whether it had limits at all. In laboratories cooled to near absolute zero, scientists trapped ions, cooled them with lasers to a fraction of a degree above absolute zero, and coaxed them into stable superpositions. In fiber optic networks and satellite links, photons were entangled across continents. Each success carried with it the same silent, humbling truth, that the most basic units of reality did not behave like things, but like possibilities. Possibilities that could be shaped, measured, and perhaps in ways still beyond human reach, understood. But the question that haunted the early pioneers of quantum theory had not faded. It had only grown sharper. If particles, molecules, even entire systems could exist in a state of everywhere at once, then where exactly did the boundary lie between the quantum and the classical, between the shadowy realm of superposition and the solid world of human experience? The next steps would push at that border, and with each experiment, the line between possibility and reality would become harder to see. In the quiet darkness of a laboratory, a single particle drifts toward its fate. There is no sound, no collision, no flicker to mark its progress. And yet in this silence, something profound unfolds. The question of where the particle is has no answer, not because it hides its position from the observer, but because position itself does not exist for it until the moment of interaction. Before that moment, it is not here or there. It is a spread of potential, a haze of probabilities governed by the wave function. This is not ignorance. It is not the same as not knowing the outcome of a coin toss. In the coin's case, the answer is hidden but real. In the particle's case, the answer is not merely hidden, it is unformed. The universe itself has not yet chosen. Time and again, experiments have shown that even when particles are sent through a double-slit apparatus one at a time with long intervals between them, the interference pattern slowly reappears. There is no second particle to interfere with, only the particle with itself. The wave of probability spreads, travels both paths, and interferes before collapsing into a single event on the detector. And the strangeness is not confined to location. Superposition can hold in other dimensions of a particle's identity, in its spin, the quantum analog of angular momentum, pointing up and down at once, in its energy state, existing in multiple energy levels simultaneously, and even, in some systems, in the question of whether the particle exists at all until interaction forces that answer. Physicists have wrestled for decades with the nature of the wave function that governs this behavior. Is it a real, physical object, a literal field spread across space with tangible presence? Or is it a human invention, a mathematical tool that encodes the probabilities of measurement outcomes, but nothing more? This debate strikes at the heart of quantum interpretation. If the wave function is real, then reality itself is extended and continuous, collapsing only when forced. If it is not, then the true nature of the quantum world may be hidden behind an even deeper layer of theory. The implications grow heavier when superposition is applied to the macroscopic world. In 1935, Erwin Schrödinger crafted his now famous thought experiment, a sealed box containing a cat, a radioactive atom, and a poison that would be released if the atom decayed. Quantum mechanics says the atom can exist in a superposition of decayed and undecayed states, and by extension, the cat can be both alive and dead until the box is opened. Schrödinger intended this scenario as a critique, a way to expose the absurdity of applying quantum rules to everyday objects. But over time, the metaphor has become a gateway into one of the deepest puzzles in science. If superposition is real at the atomic scale, what stops it from scaling upward? Why do the equations of the quantum world, so precise in describing electrons and photons, seem to give way to the solidity and definiteness of classical objects? Where is the boundary between the quantum haze and the concrete world? Today, physicists are no longer limited to cats and boxes as metaphors. In the realm of quantum computing, researchers create and sustain macroscopic superpositions in the form of qubits. Delicate systems, such as superconducting circuits or trapped ions, that can exist in multiple states at once. Here, the principle of superposition is not just observed, but engineered, harnessed to perform calculations far beyond the reach of classical computers. Yet these systems remain fragile. The slightest interaction with their environment, a stray photon, a vibration, a fluctuation of temperature, forces the collapse of the superposition.
This fragility has given rise to the concept of decoherence, the process by which a quantum system loses its superposition when entangled with its surroundings. Decoherence explains why humans do not see everyday objects in quantum states. The vast complexity of their interactions with the environment causes their wave functions to collapse almost instantly. And yet, even with decoherence accounted for, the question lingers: does collapse reflect a physical process, or merely a change in what can be known? Does the universe have a definitive state before measurement, or does it come into being through the act of measurement itself? These are not just technical debates. They are questions about the nature of reality. If the wave function is a real object, then the world between measurements is a vast ocean of simultaneous possibilities, most of which will never be realized. If it is only a tool, then quantum mechanics may be a shadow cast by deeper laws, waiting to be uncovered. The more deeply physicists probe, the more elusive the answers become. In attempting to observe the quantum world, they change it. In trying to define its reality, they find themselves altering the very thing they wish to know. It is here, at this edge, that the mystery deepens into something almost unbearable. The recognition that the act of observation is not merely the receipt of information, but an act of creation. That the smallest elements of the universe do not settle into being until they are called upon. That existence itself may be a negotiation between possibility and choice. In this realm, the question is no longer just, where is the particle? It is, when does reality itself begin? The quantum world is a theater without a single script. Its actors, electrons, photons, atoms, move in ways so alien to the human mind that even after a century of study, the plot remains uncertain. The equations are clear, the predictions work, yet the meaning of those predictions fractures into competing visions of reality. Out of this fog of possibility, 6 great interpretations have emerged, each an attempt to tell the same story, yet each painting the universe in a different light. The Copenhagen interpretation, the oldest and most widely taught view, begins with the work of Niels Bohr and Werner Heisenberg in the 1920s. In this vision, the wave function is not the world itself, but a description of what can be known about it. Reality, in the classical sense, does not exist until it is observed. Prior to that, all that can be said is that a system occupies a superposition, a blend of all possible outcomes. Observation acts as the hammer that strikes molten possibility, crystallizing it into a single, definite reality. The observer is not a passive spectator, but a participant in the creation of the event. Here, the universe is both deterministic in its mathematics and indeterminate in its unfolding, a balance that unsettled minds like Einstein's, yet remains the cornerstone of mainstream quantum mechanics. The many worlds interpretation. In 1957, Hugh Everett III proposed an audacious alternative. The wave function never collapses. Every possibility it contains is realized, not here, but somewhere. When a quantum event offers multiple outcomes, the universe splits. One branch contains the particle going left, another contains it going right. One holds the cat alive, another holds it dead. These branches do not communicate, yet all are equally real. In this view, the universe is an endless fractal of ever-diverging histories, each as tangible to its inhabitants as our own. Chance is replaced by certainty. Everything that can happen does. Free will becomes a question of which branch one experiences rather than which outcome one chooses. The pilot wave theory. First suggested by Louis de Broglie in 1927 and refined by David Bohm in the 1950s, this interpretation reintroduces the idea of determinism. Particles, it says, have definite positions and velocities at all times, guided by an invisible pilot wave that evolves according to the Schrödinger equation. The strange quantum phenomena, interference, entanglement, emerge not from indeterminacy, but from the hidden guidance of this wave. In this universe, there is no true randomness. Every motion is choreographed by the pilot wave, though humans, unable to see it directly, perceive only the probabilities it generates. Relational quantum mechanics. Proposed by Carlo Rovelli in the 1990s, this interpretation suggests that properties do not exist in isolation. Instead, they exist only in relation to something else. In this view, an electron's position is not an absolute fact. It has a position relative to one measuring device, and perhaps a different position relative to another. There is no single universal description of the world, only a network of interdependent perspectives. Reality becomes a web of relationships, where each interaction creates facts that are real within that relationship, but not necessarily beyond it. Objective collapse theories. Not all physicists are comfortable with the idea that collapse depends on observation. Objective collapse models, such as the Gerhardi-Rimini-Weber theory, propose that superposition is unstable and will spontaneously collapse after a certain time or at a certain scale, regardless of whether it is observed. In this picture, quantum weirdness rules the microscopic world, but the macroscopic realm is shielded from it by a natural built-in limit. Schrödinger's cat would not remain both alive and dead indefinitely. The superposition would break down on its own. Quantum information perspective. A more modern approach treats quantum states as carriers of information rather than direct descriptions of physical reality. In this view, the wave function encodes the knowledge an observer has about a system. Superposition is simply a reflection of incomplete encoding, an elegant summary of what is possible given the information available. This perspective aligns closely with developments in quantum computing, where the manipulation of information, rather than matter itself, becomes the essence of physical processes. Each of these interpretations describes the same experiments, the same mathematics, yet they tell radically different stories about what is. If the Copenhagen interpretation is correct, then reality is participatory. The world does not exist in full form until it is touched by measurement. The implication is unsettling. The cosmos may be incomplete without the act of witnessing. If many worlds is true, then every moment fractures into countless versions of itself, and the life one knows is but a single thread in an infinite braid. Nothing is ever truly lost, yet nothing is ever singular. If the pilot wave theory holds, then the universe is guided by hidden architecture, a deterministic framework we cannot yet see, a clockwork wrapped in mist. If relational quantum mechanics is right, then the idea of an objective, all-encompassing state of the universe may be an illusion. Reality becomes a tapestry of overlapping truths, each valid only within its own frame of reference. If objective collapses the answer, then nature itself draws a line between the possible and the actual, enforcing definitiveness in a way no observer is required to do. If the quantum information perspective is correct, then matter, energy, and even space-time may be manifestations of something deeper, the flow and processing of information itself. These interpretations do not merely shape science, they touch philosophy, reshaping humanity's place in the cosmos. Free will, determinism, the permanence of the self, even the solidity of the chair beneath one's feet all shift in meaning depending on which lens is chosen. And so, a century after the quantum revolution began, physics still gazes into a mirror that refuses to settle on a single reflection. The mathematics may describe the shadows perfectly, but the source of the light remains unseen. Somewhere between possibility and actuality, the truth waits, as silent and as strange as the first particle drifting towards its fate. Beneath mountains, in the vacuum of orbit, and in the sterile quiet of cryogenic chambers, humanity has begun constructing the instruments capable of touching the most elusive threads of reality. The quantum world, invisible to the eye and silent to the ear, reveals itself only to the most patient of observers, and only when they come armed with tools of unprecedented precision. Deep underground, in the silence of stone, far from the noise of the surface, buried beneath kilometers of rock, lie some of the most sensitive detectors ever built. Here, the Earth itself serves as a shield, filtering away the constant bombardment of cosmic rays and stray radiation. These subterranean sanctuaries, places like the Gran Sasso Laboratory in Italy or the Sanford Underground Research Facility in South Dakota, house arrays of ultra-pure crystals and vats of liquid xenon, kept in darkness and cold. They are built to wait. Days, months, even years may pass without a single meaningful signal. But when an atom in these chambers is nudged by a passing particle, be it a neutrino from the sun or some as yet unknown constituent of the quantum realm, the faintest flash of light,
pushing the boundaries of size. In laboratory interferometers, beams of particles or molecules are split, sent along separate paths, and brought back together. The resulting interference pattern reveals whether the objects remained in superposition along the way. For decades, this was a domain of light particles, electrons, neutrons, photons. But in recent years, scientists have coaxed far larger objects into this ghostly in-between state, massive molecules containing hundreds, even thousands of atoms. Each new success edges superposition closer to the macroscopic realm, where it could, in principle, involve visible objects. The challenge grows exponentially with mass. The heavier the object, the more fragile its quantum state. Heat, vibration, stray electromagnetic fields, any interaction with the environment can collapse the wave function. Yet with advanced cooling techniques, vacuum chambers, and vibration isolation, researchers continue to push the limit, seeking the moment where nature itself, without observation, may forbid superposition. The Quantum Engineer's Laboratory. Nowhere is the deliberate crafting of superposition more visible than in the rapidly advancing field of quantum computing. In these chilled, shielded machines, qubits, whether superconducting loops, trapped ions, or spins in diamond, are carefully prepared in overlapping states of 0 and 1. These states are not mistakes to be avoided. They are the essence of computation in the quantum realm. Through controlled interference, entanglement, and measurement, the quantum computer exploits superposition to process information in ways no classical machine can replicate. But the same fragility that haunts molecule interferometry plagues quantum processors. Maintaining coherence, preventing the collapse of superpositions, requires mastery over every aspect of the qubit's environment. Each success in this arena is not only a step toward practical computing, but also a proof that superposition is not merely an abstract mathematical tool. It can be engineered, maintained, and manipulated as a real physical resource. Where quantum meets gravity. Perhaps the most profound unanswered question in physics is whether the principles of quantum mechanics survive unaltered in the presence of strong gravity. General relativity, the theory that describes the warping of spacetime by mass and energy, does not easily merge with the probabilistic fluidity of the quantum world. Some theories suggest that gravity itself could act as an agent of collapse, destroying superpositions at scales too small for current experiments to detect. Testing this requires the extremes of nature, the edges of black holes, the waves of spacetime generated by colliding neutron stars. Gravitational wave observatories, like LIGO and Virgo, already detect the ripples from distant cataclysms, measuring distortions smaller than 1,000th of a proton's width. One day, their successors may be tuned not just to hear the roar of cosmic mergers, but to sense whether quantum effects survive in the presence of spacetime's most violent deformations. The horizon of experiments to come. Future missions may stretch these tests across the solar system. Quantum links between Earth and Mars could probe whether distance, time delay, or gravitational potential affects entanglement. Spaceborne interferometers could place entire satellites into delicate quantum states, challenging the notion that superposition is confined to the microscopic. In the cold shadow of the moon, shielded from solar wind and bathed in deep space quiet, detectors could listen for quantum events with an absence of terrestrial noise. And at the fringes of interstellar travel, where spacecraft skim the boundary between the sun's influence and the void beyond, measurements could explore whether the fabric of quantum mechanics itself shifts under new cosmic conditions. The tools grow sharper. The reach extends further. Yet with every test, the universe remains poised between revelation and enigma. Each experiment tightens the web of evidence, but none has yet shown the hidden machinery behind the quantum curtain. Perhaps the answer will arrive in the glow of a single photon caught between Earth and Moon, or in the vibration of a molecule impossibly split across two paths, or in the trembling of a detector buried deep beneath the surface when a particle from the heart of the universe finally whispers its truth. Until then, the quest continues, not only to measure the quantum world, but to decide what it means for the reality that contains it.
At the smallest scales, the world does not sit still. It hovers, it waits, it exists as a shimmer of maybes, a restless fog of possibility where a particle's position, momentum, even its very existence is never certain until the act of observation pins it down. This is the realm of quantum superposition, where the building blocks of reality drift in overlapping states. An electron can be here and there. A photon can travel both paths at once. Atoms can hum in two different vibrations simultaneously. It is a truth that defies the senses, yet survives every test physics can devise. If this is what matter is made of, then what exactly is matter? Some physicists suggest that this is simply the nature of information. Reality, they argue, is not a solid edifice, but a ledger of probabilities, updated when new facts are written in by observation. Others imagine a multiverse, where every possible outcome of a quantum event is realized in a branching spread of parallel worlds. Still others see superposition as a wave, not of substance, but of possibility, which collapses into something tangible only when the universe is forced to choose. And so the question lingers: does the universe exist fully and completely at all times, or only in the moments when it is measured? For humanity, the parallels are inescapable. Life itself unfolds in a haze of uncertainty. Futures stretch before us as invisible branches. Every unmade choice, every unopened door, lies dormant in its own form of possibility. And like the particle in superposition, our paths crystallize only when we act, when potential is traded for history. In this way, superposition is not merely a property of electrons and quarks, it is the human condition mirrored in the physics of the cosmos. Some philosophers and scientists have wondered whether consciousness plays a deeper role. Could the act of observation, the awareness of a result, be the very thing that pulls reality from its cloud of uncertainty into the single outcome we experience? The mainstream view denies that a human mind is required. A Geiger counter will collapse a wave function just as well as an eye. Yet the connection remains haunting. The observer and the observed, locked in a dance neither can seem to escape. Perhaps the universe does not merely allow consciousness to exist, perhaps it needs it, as a mirror needs light to reveal its reflection. If the superposition principle is fundamental, then reality is not the hard, cold machinery it once seemed. It is something softer, stranger, more like an ocean than a clock. A vast sea of potential, its surface calm yet filled with unseen currents, each ripple a possible event. From afar, it is a featureless expanse, smooth, unbroken. But when a wave reaches the shore, when possibility meets the edge of observation, it crashes into form, into the here and now. In that moment, the infinite becomes singular. The maybe becomes the is. And so, the closing thought lingers, like a question carried on the tide. Perhaps the universe is not a thing that exists, but a question still being asked.